Okay, I welcome everybody to this first session during this afternoon, session 4. This is a session that is in particular, I think, dedicated to the work that is done in Lugano in Jürgen Schmidhuber's group. We have several talks, well, no, nearly all talks are from Lugano, so to speak, and we start our first talk written by Tobias Glasmachers and Jürgen Schmidhuber. The title is Optimal Direct Policy Search. It's all yours.
Thank you. I don't know why they put all our talks together like that, but it's fine with us. This should have been done by Tobias Glasmachers, who is now with his family, who couldn't come, and so I'm going to try to be a substitute there. We will have several talks in this session that range from very theoretical stuff to rather practical stuff. For example, in a couple of minutes, I hope I will be able to talk about how to use very practical methods, neural networks for winning all kinds of traffic sign competitions and pattern recognition competitions. But now this is a theoretical thing, and it's about optimal direct policy search. To understand what is going on, what is the topic of this talk at all, it's good to recall what is the difference between traditional reinforcement learning and direct policy search. Both can be used to maximize fitness or reward functions in many situations. Now, with reinforcement learning, you really have the general approach. You act, you perceive, you act, you perceive. As you're doing that, you're building a better and better model of the world, and you can then use this model of the world to compute action sequences that maximize future expected reward, and any problem can be formulated in this framework. Important with with general reinforcement learning, you can predict things that happened never before, and as an example, consider that we today can predict that at some point the sun is going to explode, although it never did before, and we can already plan for that event. Now, direct search is more limited because there you assume these repeatable trials. You perform your action sequence based on your current policy, maybe a couple of times to gain statistical reliability, and you then evaluate your policies based on the achievements during these repeatable trials, and you try to come up with better and better policies using some policy search method, which does not really predict the future. While reinforcement learning of the general type is more general than direct policy search, almost all the benchmarks that are being used in reinforcement learning, like, for example, the helicopter flying problem, or the mountain car problem, or the car racing problem, and all these things, they can be solved easily, well, not easily, but they can be solved by both types of approaches. So most benchmarks do not reflect that there is a general type of reinforcement learning which is more powerful. Here I'm going to focus on tasks that can be solved by both, and the optimal direct policy search, which we are going to discuss here, is in principle rather simple. It's inspired by the universal search techniques that Leonid Levin developed in, I think, 1973. We are going to translate programs into policies, which are essentially probabilistic ways of acting in the environment. Probabilistic, well, it's a program essentially that determines the probability distribution of the possible actions that you as an actor can draw your actions from as you are interacting with the environment. And like Levin search or universal search, we iteratively and exhaustively go through program space, but in a good way. We start with very small programs and don't run them for too long, etc. And we keep growing this procedure. The programs get longer and longer, the runtimes get longer and longer. And essentially what's happening there is that each program that we are testing gets a fraction of the total runtime allocated, which is proportional to its probability, where the probability of the program is essentially 2 to minus n, where n is the length of the program. So that's essentially the probability of guessing that program if you had a fair coin. Now, the practical way of doing that is you have a sequence of phases, and in the nth phase, you test all programs that have the property that their size plus the logarithm of their runtime does not exceed n. For example, in the 10th phase, you test all programs of size 3 for at least 2 to the 7, for at most 2 to the 7 time steps, and all programs of size 5 for at most 2 to the 5 time steps, etc. Now, what is not there in the original formulation of universal search is a good way of dealing with stochastic evaluations. It can be shown very easily that universal search is going to solve any quickly verifiable problem as quickly as the fastest algorithm that solves it, the unknown fastest algorithm that solves it, say for a constant factor, which is essentially the probability of the program that solves it fastest. So it's that's why it's asymptotically optimal. Now, if you have stochastic evaluations of your policy, you never know exactly, isn't that just an accident that I got a high reward now in response to that policy, and you have to do it a couple of times to gain reliability. And we are doing that in a good way. And the way to do that essentially is we are going to explore by searching in this space of programs. However, as we are exploring more and more, we are also increasing the time allocated to exploitation of the best policy found so far, essentially. And the way to do it is justified by this little theorem, which essentially says that if we do it the way it is described in the paper, then we can guarantee that as we are increasing the number n, which is the index of the programs that we are testing, we are going to end up with a policy, with a global strategy that is going to converge in its reward intake towards the optimum that you can obtain. And this is true. The theorem holds for certain technical assumptions. And these assumptions essentially are that the episode length, which can vary greatly as you're testing this policy under several under several different circumstances in your environment, that the episode length or the mean of the episode lengths is finite, and the variance as well. And the same should hold for the rewards. The mean of the rewards should be finite, and the variance should be finite. If that is the case, then this method is going to converge. And here's a little illustrative example. We are not claiming that this is a very practical method in many applications, but this is an illustrative example where you see lots of little states. Now, each of these little circles here represents a state, and you start in one of the two states in the left upper corner. Now, in each state, you can make a binary observation, either black or white, or 0 or 1. And then in each state, you have two actions, action 1 and action 2. Now, if you are in the white region, in one of these white stripes, then action 1 will take you left, and action 2 will take you right. However, in both cases, you don't know exactly where you're going to end, because there are two arrows going from each state to the left, and also two arrows going from each state to the right. Now, if you are in a dark stripe, then this is reversed. So action 1 means then just the opposite of action 2. And because it's very, very stochastic, in 30% of all cases, this rule that I just described doesn't hold, but you just get the opposite effect that than what I just described. Now, the goal is to end up at the goal, which is to the right. And this is a partially observable Markov decision problem, because in every state you have only very little information about where you are, and you actually have to take the history of previous visits of previous states into account, previous observations into account, to come up with a good strategy to traverse that as quickly as possible. For every step that you are using, you get a reward of -1, which means you are motivated to maximize external reward, which means that you are motivated to go as quickly through this maze as possible. And then instead of using a universal Turing equivalent programming language, we are just using a search through the growing string of previous observations. So first observations of size 1, then of size 2, then of size 3, and so on, until we get sufficient data from the history to solve that particular problem using the scheme which I just described and which is described in detail in the paper. So this is just repeating what I just said. And then you see at this in the slide how in the lowest line you get the total average fitness, which is the combination of the exploitation and the exploration, which are running in parallel. Now the uppermost line with the narrow dots is what you get during what you would get during pure exploration. The dark line that you see in the middle is the exploitation fitness. That is what you would get if you always took the best thing that you found so far, and you see that this thing is quickly converging to the best possible thing. Only in the beginning, for the first 25 or so steps in this case, we have a significant difference and overfitting, because the exploration behaves differently from the exploitation, but quickly they converge, and after a couple of trials the task is really solved. So we have something that is a policy searcher which is even under stochastic conditions of a very general kind going to end up with the optimal policy in all of these environments of this type that satisfies these conditions, and that's good. All right, thank you. Next one.
Okay, thank you very much. Our next talk, the title is Planning to be Surprised, Optimal Bayesian Exploration in Dynamic Environments. Paper was written by Yi Sun, Faustino Gomez, and Jürgen Schmidhuber.
Okay. This title is Planning to be Surprised. It's basically about optimal Bayesian exploration. We use some quite simple stuff here. So some preliminary background. So basically that you can imagine an agent is sent to explore the environment. By exploration, we mean that there's no external reward. So basically the agent sort of interact with the environment in sequential orders. We only assume one-dimensional time. And it is basically limited by time or resources. So in this case, you can ask essentially a question. Well, there's an example that if you're familiar with the Markov decision process, you can basically think this problem as if you have only 100 actions, how do you actually do in that environment so that you can learn the transition probability of the Markov decision process as quickly as possible? Then you can sort of generalize this to like an arbitrary environment. Then you ask this general question. Basically, it's how should the agent choose the actions so that it learns the environment as effectively as possible? So this is the question we're trying to answer. So there are basically two terms in this question. One is what does it mean by learning, or the other one is how to measure the efficiency. So we adopt some rather classical framework. So here the learning is through probabilistic inference, and the effectiveness is basically measured via Shannon information gain when we use this model of complexity here. So more detail, the agent we assume this agent interacts with the environment in time cycles t equals 1, 2, and at each time cycle it basically performs an action, then receives observation that can be defined in some general spaces. And we repeatedly use this terminology called history, which is basically either it's an empty string or it's some history padded with an action observation pair. Here this H prime AO just means you concatenate the two string, like H prime and the action observation pair. So we make this key assumption which enables us to do this to do all the following derivation. So we assume there's a random element of theta that describes the environment, and with known prior p theta, which that means that you know something, like there's a probability distribution and some measurable space. And then we know that the predictive probability P O given HA and theta. So that means once you know the model exactly, you can predict what's going to happen. And once you make these assumptions, the learning problem is kind of straightforward. You can just do the learning through probabilistic inference. And here the tricky part is that you see that there's a P theta given HA. That basically means that you want to update your belief after you observe a history H and additional action A. But knowing the action A without the consequent observation would not change your belief. You can think of this as throwing a coin, but not knowing the result of the flipping, or not knowing the result will not change your belief about this probability of showing head. So about measuring the learning progress. So consider H and H prime be two histories, and I use this sign to say that H is a prefix of H prime. So H prime has some additional action observation pairs. So we measure this learning progress essentially through information gain, which is defined as the K-out divergence between the posterior distribution of theta in two time steps, which is given by this formula. And it's this information gain basically quantifies the unexpectedness caused by the additional action observation pair H prime, exclude H. So additional action observation pair cause your information to change, and this information gain quantifies how much you gain from this additional information. And then we can define this expected information gain, which is, this is actually the one-step expected information gain, as the expectation over the information gain, provided that you can only do one actions, and then you predict the observation according to the current posterior. So this expected information gain basically quantifies the potential unexpectedness when you perform some action. And the key property here is that the action with high expected information gain allows one to learn more in one step. So you choose an action with high expected information gain that on average will allow you to probe more into theta, the environment. So because the agent sort of interact with the environment in sequential order, so we consider this sequential Bayesian exploration problem. So we approach this problem in a certain sense that assume now you already experienced some history H, which might be empty. Then you have a policy, like exploration policy pi, basically map the history to some kind of probability over the possible actions, and assume you're going to make another tormal actions. So how do you sort of plan these tormal actions? The center definition here is what we call curiosity Q value, which is basically the multi-step expected information gain from performing the action at the current step, then you're following the given policy for another pi minus 1, tau minus 1 steps. And then based on this, you can define the curiosity value, just like in reinforcement learning, as the expected information gain from following the policy for 2 more steps. So basically, this is expectation of the curiosity Q value, assuming A is drawn from the current policy. So the property of this curiosity Q value or curiosity value is the policy with the high curiosity Q value learns more in expectation. So on average, if you follow a policy with higher curiosity Q value, you're in expectation getting more information from the environment. And a particular nice property of this curiosity Q value is that it has this recursive decomposition, which is pretty nice. You can link the Q pi tau with V pi tau minus 1 or Q pi tau minus 1. That means that you can sort of cascade these Q values or recursively decompose these Q values. And this decomposition also shows that if you want to have a good policy, it has to balance between the immediate expected information gain and then the information gain you hope to get from the situation where you end up with. So that requires planning. And this decomposition is actually not so trivial. It's a consequence of using K-out divergence. So if you use F divergence or Bregman or general divergence, it doesn't have this property. And it's similar to value function in reinforcement learning, but with some subtle differences, actually not. Because the information gain is additive only in expectation. You cannot go back and add up those information gain. It doesn't make much sense. So once you have this decomposition, you can define the optimal exploration policy. And the policy which is optimal turns out to be the greedy policy if you just maximize the curiosity Q value for any history and future look at the steps. In particular, well, I already said that acting greedily is the optimal policy. So in particular, we have a small theorem here. Well, then you can recursively define the optimal accuracy Q value. Then you choose your actions greedily according to that accuracy Q value. Then you end up with the optimal policy. This is basically this theorem thing. And the optimal policy is defined constructively for finite lookup steps. That means you can, in principle, follow this theorem and do it, but it's intractable. Well, the good news is for finite Markovian environment, this optimal policy can be well approximated through dynamic programming. That requires additional proof that you can find in my homepage. There's a tech report with quite long proof, but you can approximate it well in certain environments. And here's an illustrative example that you have a two small world on the left part of the graph that connected through a very long corridor. So you have 2 clicks, then there's a very long corridor. You have to move back and forth to get to the interesting part. And then there are 4 different exploration strategies considered. So the random didn't get you very far because the random walk is quite slow along the corridor. And if you use the expected information gain as the reward and then you do Q-learning, you're basically getting nowhere. And if you take the greedy action, basically you only maximize the immediate information gain. You get to the other part of the world, but it takes a long time. But if you do this dynamic programming, you essentially move back and forth inside this environment. Well, in this figure, the lower part and upper part sort of corresponding to the 2 click, and the part in the middle is the corridor. Well, and here's as a result, the accumulated information gain depicted in this graph shows the difference. So the DP dynamic programming based exploration has very high cumulative information gain, especially in the early phase. And you can see this greedy exploration is also going quite well, but it's slower. Then the random is even slower. Then if you use Q-learning, you're basically stuck in one side of the world. So the cumulative information gain a long time basically doesn't increase. Well, it finally happens. Okay. Yeah, that's it.
Thank you very much. Next talk, Tom, Schaul, Pape, Tobias, Glasmachers, Vincent, Graziano, and Jürgen Schmidhuber, Coherence Progress, a measure of interestingness based on fixed compressors. So
thank you very much. Okay, so as was just mentioned, this is joint work with Tobias Glasmachers, Leo Pape, Vincent, Graziano, and Jürgen Schmidhuber. It's going to be a slightly less technical talk than the previous one, and it's going to be about what is interestingness and how can we measure it. And so I'll start by making you take a step back and think about how would you define interestingness and how would you think it's possible to measure it. And it turns out this is a problem that psychologists have been thinking about for quite a while, like over 100 years. And here's a qualitative result of what they have been saying. Is basically you can link interestingness to novelty. So if you have something that is not novel at all, it doesn't have any new information content, it's probably also not going to be very interesting. So that is the left end of the spectrum. On the other hand, if you have something that is too novel, that is, so for example, a book that is written in a language you don't yet understand, it will be incomprehensible. So there's too much novelty for you to find it interesting. And so there's a sweet spot just in between. For example, like a talk like this one, which I hope is novel enough, but then not incomprehensible. And so there's one additional thing to note, that this measure of novelty is a subjective one. So it depends on the observer. Not everybody has had the same lifetime experience. Not everybody has seen the same history of observations. And so this curve will look different for every agent. And in, more than that, it will also look different for the same agent at different points during its lifetime. So once you learn this new language, the curve will shift, and something that was incomprehensible before will maybe now be very interesting. All right, so now we have a quantitative idea of what interestingness could be. Now let's try to see how can we make this we had a qualitative idea. How can we make this quantitative? How can we get a measure that we can use in artificial agents that is a numeric value of interestingness? And so there has been a lot of interesting work in that direction. One of the prime examples being compression progress by Jürgen. And in that case, we have a learning agent that has some kind of compact representation of its experience. And we're going to look at how compact this representation is. And we're going to say, okay, whenever the agent manages to compress more, so there's compression progress, then it did something interesting. So if it sees something that enables it to understand patterns in the world and allows it to compress it down to a simple rule, let's say it discovers gravity, and then all those phenomena that are based on gravity become compressible to a simple rule, then that was something very interesting. And so there's two different sources for interesting events. One is basically new data. You observe something new that is helping you compress and is therefore interesting. The second source is learning progress. It's basically a thinking step where you revisit your experience and think about it, do some processing, and that allows you to compress it more. So there you also get compression progress. So that is also something interesting. Now in this paper, what we're going to try to do is disentangle those two sources and try to see if we can find a measure of interestingness that is only based on the first, that doesn't assume learning. So we're going to look at the interestingness of data and data alone. And so, of course, always in the subjective scenario, based on the previous data, the history that we had. And exactly, so no learning being involved. So we don't assume a learning agent. We're just going to try to base the measure on the data itself. And even in that case, what we argue in this paper is that there are still some sequences that are more interesting than others. And in order to do that, what we're going to use, again, is the principle of compression. And the result that I'll present how it works is called coherence progress. So as a preliminary, let's look at compression and compression similarity. So let's assume you have two items, and there's two possible ways of compressing them. One is to compress them separately, each one without the compression algorithm being involved when the other one is compressed, or to compress them together and make use of potential overlap between the two. And this very simple idea is a way of, it's one possible way of defining a compression similarity. So it's a measure of similarity between two things based on compression. So it's basically the compressed length of the first object and plus the compressed length of the second minus the compressed length if you compress them at once. So this is our similarity, S sub C. And now we're going to introduce this new concept of coherence. And coherence is basically the expected or average compression similarity over a whole set. So whereas compression similarity was a measure between two items, now we're going to have a measure on a whole set. And so this is just the average over all possible partitionings of the of our set, H. And as an interesting measure, what we're going to use is the coherence progress. So how much this coherence increases after new observations gets added to the set. So the data changes, something new gets added to the set, and we want to determine how much does that increase the coherence. So after that new observation comes in, can we compress the different components of the set together in a better way? So that is the intuition. That's the coherence progress. It's basically just the derivative on this coherence measure. So that was it already. That's already the whole formulation. There's some details in the paper, but let's see if our intuitions, the qualitative intuitions, match the formula. So what we would like is that an observation that is blank, that doesn't contain any information content, also doesn't introduce. It's not an interesting observation, so we don't want it to introduce coherence progress. And indeed, that's what we get out of the formula as well. If the observation is random, again, as it is by definition then incompressible. It is also incompressible when compressed together with items in our set, so it won't help. It won't increase the coherence. Similar for an unrelated observation, which is something. Let's say you have all items are in one language, and then you add one that is in a completely different language where there's no overlap. Then that won't increase the coherence of the set. At least not the first item in that language. Later that might then work. And what we would like is that if you repeat something you did before, that might be interesting, but there should be some kind of decay. You don't want to get an agent that tries to do interesting things and always keeps on repeating the same things, which sounds like something humans do as well. And so we actually get from this formulation, we get an exponential decay on repeating items that are in the set already. And then all other cases, we have a strictly positive coherence progress. So this is just a small demonstration. There's a couple of those in the paper. This is a demonstration using Wikipedia articles of animals. So our original set contains the article of human and just the text. And then we add new observations, and new observations are articles as well. And we are adding them based on which one is the most interesting. And so we're measuring this coherence progress with respect to all the potential articles, which are other animal articles, or animal articles we already know, or empty articles with no information content, or random scrambled text. And so what we would like is that this kind of algorithm does indeed go for new animals all the time, and that is what happens, so that is good. And those are the results. So they're the animals that increase coherence progress most based on how they are written in Wikipedia currently. So not so surprisingly, the first one is chimpanzee, because there's a lot of compression similarity between that one and human. And then the next most interesting is hippopotamus, and then jaguar. I don't know if that's it's hard to evaluate how truly interesting those animals are, but they are at least not the most uninteresting ones in the set. So, all right. So that's already my talk. Let me conclude. So what we did is we introduced a new quantitative measure of interestingness that is based only on compression. So it doesn't require this assumption of a learning agent. So you can just use it and apply it to data streams directly. And it's a very simple formulation. And it happens to at least qualitatively match what we expect from an interesting measure. All right. Thank you very much.
Thank you very much. Next presentation is entitled On Fast Deep Nets for AGI Vision. Jürgen Schmidhuber, dann Ciresan, Ueli, Meier, Jonathan, Masci, and Alex Graves.
I'm going to talk about now about the second neural network renaissance, which is currently ongoing, and I'll try to show you how you can win all kinds of pattern recognition competitions using our special breed of deep or recurrent neural networks. AGI is driven by two types of progress, at least. On the one hand, we have these new millennium results on optimal universal problem solvers that are theoretically unbeatable and mathematically optimal. But then we also have another type of progress driven by hardware advances. Computers are still getting faster by a factor of 100 or 1,000 per decade per cent. And this is what we are going to use in this talk. A long time ago, 20 years ago, my first student, Sepp Hochreiter, he showed that you cannot really train deep networks with many nonlinear layers or deep or recurrent networks, which you can translate into deep feedforward networks, which have as many layers as there are time steps in the sequence that you are processing, because there's this vanishing gradient error problem as you are increasing the number of layers, nonlinear layers, to which you are propagating in these networks. Every time there's a new layer or a new time step, you decrease the error signal by at most a particular constant factor, which means that after it vanishes exponentially as you are adding layers and time steps, which means that you cannot really propagate far down in traditional networks like this. This prompted one of the pioneers of neural networks to say that nobody in his right mind would take a deep multi-layer perceptron and train it by backprop. I won't mention this pioneer by name, except to say that he is Geoff Hinton. So nobody in his right mind, that seems like an accurate description of our neural computer vision team. Here we see Dan and Ueli and Jonathan and Alex. And so we took a deep multi-layer perceptron with many layers and trained it by backprop. Although my own lab showed that you shouldn't really do that. However, something has changed because now computers are a million times faster than they used to be 20 years ago. And suddenly we can propagate errors down a little bit further than we used to. And now we can have as many layers in a deep network as are connecting our retinas with the visual cortex, 7, 8, 9, nobody knows exactly, something like that. And we applied that to the most famous benchmark of machine learning, which was developed in the lab of another pioneer of neural network of Yann LeCun in New York. And there's a long history of broken benchmark records on this problem, and many people use all kinds of support vector machines and whatever. However, our approach achieved a new world record just last year. And then we greatly profit from graphics cards, which makes everything 50 times faster than on traditional CPUs. Now, you can further improve this result if you take not only one deep network like that, but you can take 7 or 10, and then each of them is slightly differently initialized and maybe has slightly different pre-processing, and you get different experts automatically as a byproduct, as a random byproduct of that, and then you do a democratic committee which just takes the average of all these predictions of the different networks, and the result is better than any individual network, and this led to a new world record on the same data set, which is now 0.31%. And what you really should do is take not plain backprop, but something which is combining all kinds of ideas that range back to Fukushima, the neocognitron, and max pooling, which is a way of downsampling from one layer to the next, and convolution and weight sharing, where you have not as many free parameters as you would have in a plain deep network. And then the current world record on that MNIST problem is 0.27%. You can also do other images with that. For example, this is the CIFAR object recognition problem of Geoff Hinton's group in Toronto. And there we also just a while ago broke the record on that one. And the current one, which is not even published yet, is now 13% on this one here. There you have to distinguish frogs from cars and horses and boats. I have a lot of problems with the frogs. And just a while ago, Ueli and Dan, they were instrumental in winning the Chinese handwriting recognition competition, where we used exactly the same approach. Now, that's an interesting problem because unlike with MNIST, for example, you have not only 10 different patterns, but 4,000. And there we got the first and the second ranks. That was just 2 months ago. And if you look then at the details of these feature detectors that are being learned automatically as a byproduct of these deep networks, you see the stuff that you know from vision of decades ago. You get automatically you get Gabor filters and on center off surround detectors and orientation sensitive bar detectors in the lower layers, and as you are looking at feature detectors in higher layers, they get more and more opaque and intransparent and less clear what's going on there, just like in human brains. Now, we applied the same thing to the NORB object recognition benchmark and also set a new record. So I'm sorry, my slides are going to remain boring like that for a while, but then they will become boring in a different way. Yes, the traffic sign competition that took part in January, there was an online traffic sign competition, and our toughest competitors usually are those from Yann LeCun's lab. It's interesting to see that only neural networks are now playing a part in these competitions, and no support vector machines, no boosting and all these things. It's a competition mainly between networks now, which is kind of unusual or unexpected because 10 years ago, neural networks almost vanished from the scene because support vector machines were so much better in many applications, and for a long time it was not possible to publish anything at the leading neural network conferences that had the word neural in the title. And there, on the last day of the competition, where we thought we have a comfortable lead, then suddenly Pierre Sermani of Yann LeCun's lab, he had an even better result, and then Dan and Ueli and Jonathan worked late night to reestablish the correct order. And then the best teams of that time, they were invited just a couple of days ago to the IJCNN conference, where the goal was to take the new data set with more data and then participate in the final competition. And down there we see Dan with the #1 traffic sign that you can see in his hands. There the differences were unexpectedly high. So Pierre Sermani, this time of New York University, of Yann LeCun's lab, achieved 1.69% correct. Then the second best were the humans. Humans are able to get 1.16% correct according to the conference organizers, and first place for our team with 0.56% error. Now this might be of interest to everybody who is doing self-driving cars, and of course we all remember this incredible keynote of Ernst Dickmanns, who is not using GPS for self-driving cars, but is doing it in the human-like way, and in 1995 already used these active vision systems to drive from Munich to Denmark and back in traffic with up to 12 vehicles surrounding the car and tracking them all using these. How many people saw this talk and how the camera swiveled along there? The active vision camera. I think this will also be the future of self-driving cars, in addition to GPS and radar and LiDAR. But to do fast driving, you just have to ask Ernst Dickmanns. You need these active vision techniques for getting high resolution input of stuff that is far ahead. As you are driving fast, you need to look far ahead to be able to brake in time if there's an obstacle on the street. And so LiDAR or something like that is not sufficient. Now, once you have identified salient points, then you still have to do the traffic sign recognition or pedestrian air recognition or whatever you want to recognize there. And there, at the moment, I think I can recommend this technique. Now, of course, in the long run, we don't just want to recognize patterns that are single patterns by feed-forward networks. No, we have streams of patterns, videos essentially, where there is no segmentation, where nobody segmented the stream into relevant parts, and to do that, we cannot use feed-forward networks. There we really have to use recurrent networks, which are general computers, and one of the examples of applications is connected handwriting. Connected handwriting, there somebody scribbles something and you are supposed to translate that into plain text, which means you have a rather short label sequence. However, you have a long real-valued input sequence of pixels that you are sequentially observing, and there you need a recurrent network, and preferably a long short-term memory network that can really deal with these long delays between relevant events. And Alex Graves, my former PhD student and then postdoc, who is now going to Geoff Hinton's lab actually, he used this approach in conjunction with a technique called connectionist temporal classification, which maximizes the probability of the label sequences given these long real-valued input sequences without any pre-segmentation, and then applied that to various handwriting recognition competitions, connected handwriting, and so that's how he won the French connected handwriting competition, and the Farsi connected handwriting competition, and the Arab connected handwriting recognition contest without speaking any word of Arabic. You may have guessed that that the Swiss AI lab is in Switzerland, and in Switzerland, traffic signs are really important. If you don't obey a traffic sign in Switzerland, you go to jail. However, across the border there is Italy. And in Italy they also have traffic signs in the street, however only for decoration. Well, we are currently trying to write a book about things like that, and I think that's the end of my talk. Thank you.
Thank you very much. Next talk entitled Sequential Constant Size Compression and Reinforcement Learning. The authors are Linus Gislen, Matt Luciev, Vincent Graziano, and Jürgen Schmidhuber.
Okay, so the title of my talk is Sequential Constant Size Compressor for Reinforcement Learning. And it's, as you know now, part of the work of ITSES group in Switzerland. So we try here to do maybe more practical, small step against AGI. We thought about this idea that Pollack had in 1990, so more than 20 years ago, which is called recurrent auto-associator memory, which was used in the context of natural language processing. And it can, in principle, compress agents' entire history in a spatial code. But it's not... we need something more than it's not enough to remember all the history. We also need some reinforcement learning on top of this to actually do meaningful actions. So we put this on top of this RAAM network. And also a part of this is to use the information that we get in a meaningful way. So we don't want to use information that is has no real valuable information. So we use some kind of exploration and exploitation drive. So the idea for this is to, on the bottom of this system, we use an autoencoder, which is optional. We will use this for one of our experiments, but not for the other. And after this autoencoder, we feed the visual input into this system, this RAAM, which can now then compress the spatial and temporal features and essentially build a code of the entire history. And then we use some trick, which is called a vector quantization. I will go through what it actually means for those who haven't seen it before. And then on top of that, we use Ciresan, which uses this vector quantized representation. We call this system servo. So first explanation a little bit how RAAM works. So in principle, it's an autoencoder. I don't know if you all know that, but you see to the left bottom, you see the network itself. It consists of input layer, arbitrary size, and then a hidden layer, means H1 there. The 1 stands for the time, so it's time 1. And it can be arbitrary size 2. And then the output or the target is supposed to be a reconstruction of the input. And the input H0 that is actually the previous time step of the hidden layer. So when this goes through time, this hidden layer will be sent back and be used as input again. And then it will compress that, and then it can repeat that. So for every time step, we build up a representation of all the previous state and actions. And in the end, in H3, we have all the previous time step in a compressed manner. And in order to see how this works, we need to decode this. So we just take now the upper part of the system, and we feed in H3 now. And as this system has learned to reconstruct the observation and action, and also the previous hidden state, we can get out from H3, time step 3, we can get out the time step 2 plus the observation. And then we can send in that back in the system and get another observation from that time step. And we repeat this until we get all the observations out of the system. And this can be arbitrarily long, so containing all the lifetime, more or less, of an agent, in principle. And on top of this, now we use a vector quantization, where we use the output from the hidden layer. And it is used because we have a lot of noise in our input. So it will just make it group together the different state that actually belongs together. And so we do two experiments. The first one, we use a maze that looks like the picture to the right there. That's the top view. The agent's view is the only thing that the agent sees. So it doesn't see the top view at all. It just sees looking forward in this maze. And you can see a little bit, it's a bit noisy, but you can see the walls. There's some texture on the walls and the end of the corridor. And it's supposed to reach G, which is the goal. And it's placed randomly. It has 250 actions to solve its task. Otherwise, it's taken back out and put down at a random position again. It has 4 actions can move forward, turn left, turn right, turn 180 degrees. And the input is 160 pixels. So here's some technical details how we train this. We use a normal backprop, learner rate 0.01. For the SARSA, we use eligibility traces, learner rate 0.1, and decay rate of 0.8, and the trace decay for 0.9. And we shift between exploration mostly, or 50% exploration, and we go down to total exploitation of the agent. So when it learns a policy, it would stick to that no matter what. And we can find that the agent can find an almost optimal solution. I put it in these tags because it has to learn first what it is to actually take the optimal step. And it can find out where it is by moving around in the maze itself. And we compared this to SNES, separate natural evolution strategy. And there's a method that through neural evolution builds a recurrent network directly on the pixels or in the input itself. So the idea is that the agent gets implicit feedback between the unsupervised learner and the reinforcement learner by slowly learning to compress the environment better, because when it can compress the input in a better way, it can give also more useful information to the reinforcement learner, which can then take more valuable actions. So the unsupervised learner can learn to compress its environment better. So it improves iterative. And for the second experiment, we also want to include a long temporal dependency. For the former, it was just needed 1 or 2 steps history. But in this case, it needs up to 12 frames to learn where it actually, in which state it is in. So this is more or less a long corridor without door in the end. It starts at t equals 1, and it moves, it has 2 actions. Either it stands still or it moves towards the end of the corridor. And when it gets to the door, it gets a signal on the wall. It sees A, B, C, or D, and each letter represents a time, which is supposed to wait. And for D, for example, it needs to wait 12 time steps before it moves through, otherwise it won't get a ward. So you cannot exit too early or too late. And the technical details here is we use backprop and also SARSA here again. And we use a random walk to collect samples, but we only use the successful episodes. And it can, this is average of 10 different agents, and it turns out it can learn up to about 95%, but then it will make some mistakes because the noise can cause problem for it to actually exit at the right time. I will show a short video how it looks. I can get this. So this is during the learning episode. So it moves down the corridor and it tries to exit. And when it gets this red signal, it's exit at the wrong time. So sometimes it doesn't even know that it has to move forward, and that's when you see it stands still. And so it needs to learn to move forward, wait for the right time, and then exit. And we'll see how it looks when it actually has learned something. So it gets a green signal then. And then, for example, in this case, D, now it has to wait for 12 time steps. And you can, if you actually count quick, you can see that it actually does the correct waiting time. And B means it has to wait for 8 time steps in this case. Okay. Okay, so this is maybe not could be yet completely practical for mainly 2 reasons. That one is that it has no attention. It tries to reconstruct everything it sees. I mean, that could also be an advantage, but in this case, it could be a disadvantage because of the noise. It tries to reconstruct all the noise and stuff like that. We also have a moving target, which is an inherent problem with this RAAM architecture because it tries to reconstruct the system itself, and when it does that, the system itself changes. So it can never get to a perfect representation of itself, because then it will change already. So, but to conclude, we have shown that it can successfully deal with high-dimension observation and also deep memory requirements. It can, in principle, code entire history of agents' lifetime, depending on how deep or how big your hidden layer is. But of course, as the hidden layer grows larger, the harder it is to train too. And we also show that the system decouples the problem of encoding the relevant spatiotemporal regularities from learning how to act on them. Okay, and with that, I'm done. Thank you.
Okay, our last talk for this session, Derek Morner and James Regia, systematically grounding language through vision in a deep recurrent neural network.
Good afternoon, everyone. Can people hear me? Okay. Fair enough. So I'm not from IDSIA. It's an important point. I think I'll get to a point about halfway through the talk where I can maybe explain why I was picked to be up here and what I've been jokingly referring to all weekend as the Schmidhuber session. But I'm here to talk about a neural network model we've come up with to try to get at some of the keys that we think are important to general intelligence. So the first is obvious, and we've participate in discourse, and we might not all agree that this is a good test or a good requirement for general intelligence, but I think we can mostly agree that it's a good start because, you know, it's the same kind of test that we implicitly give to each other every day. So I won't talk too much about that one, but I do want to move on to a second point, which is taken from the cognitive philosopher John Searle. His Chinese room thought experiment from decades ago it had the point of trying to tell us that symbol manipulation alone is not enough to give us general intelligence. So the easiest way to think about that is to think about looking up a word in a dictionary. So if you start with a word and you want to know what it means, you look it up in a dictionary, and you get a definition of it in terms of other words. And of course, if you don't know what those mean, you have to look those up and get more words. And this can kind of get out of hand very quickly, and you end up with an infinite regress if you don't know any words in the language that we're talking about. So the way that humans solve this is by taking some of these words and grounding them, which is to say relating them to other things that we see in the world via other senses. So Searle's point, and the point that we want to drive home about grounding and embodiment, is that humans ground language in their other senses, like vision, and if intelligent machines are going to interact with us, then they're going to have to do the same thing. So the third and final key point that we wanted to address with this is something that Fodor and Pilishin would call systematicity. So it's kind of related to both compression and abstraction, which we've discussed at this conference a lot already. But it's operationalized. It's that same concept, but it's measured only by performance. The idea is that human understanding of certain situations is kind of intrinsically tied to understanding of other similar situations. So one way to think about that is to think about trying to interpret, classify a big set of objects like this. You might say that, those three are large and those three are red, and those three are pyramids. And what the systematicity people would say is that if you really understand this in a systematic way, you should be able to look at an object that you've never seen before and kind of abstract out the largeness and the redness and the pyramidness and be able to describe this novel object, with a phrase that you've never heard before. Maybe you've never heard of a large red pyramid, but if you understand these concepts, you should be able to put this together. So this is not a problem generally for these higher level symbolic models that kind of build systematicity in, but neural networks in particular have had trouble with this over the years. So we figure if we can get all three of those, kind of get on that road, we can start potentially building an AGI with a neural network. So I'm gonna show you a model that we've made that starts down that road. Here's the kind of the zoomed out version of it. The idea with what we're trying to do here is take a neural network and get it to learn to interpret sentences that it hears in terms of a micro world that it sees. So it kind of has two major sources of input. One is visual, and that input comes in the form of a scene, which is just a collection of objects that are presented temporally. Each of these objects has three attributes: a size, a color, and a shape. It also has a unique identifier in case we need to distinguish between two similar objects. The second source of input is auditory, and we call this the sentence. This consists of a sequence of phonemes, each phoneme being represented as a bundle of auditory features. So the network will see somewhere along the lines of 20 to 40 phonemes come in temporally as a sequence. And these, if you sounded them out, would produce a sentence in English that is talking about the scene that the network has just experienced. And then the job of the network is to produce a sequence of predicates that's going to encode the meaning of what was said in terms of the scene. So we'll try to concretize this a little bit by going through an example. So if we have the scene that you see at the bottom here with these objects, you can take a look at the visual input on the left there on top, where we have a small red pyramid, object number 1, a large blue block, object number 4. That would be the scene, and the network is going to digest those into its working memory. And then the network will hear a sentence. So the example sentence here is the small pyramids are near the blue block. And of course, it doesn't see that as words. It sees it as one long, uninterrupted sequence that is not pre-segmented at all. So it has to, not only figure out that there is such a thing as a word in here, but it has to pick out the words, segment them out, figure out what they correspond to in terms of the visual environment. And then as far as the output goes, the intention stream on the right there, the network is going to produce, for this sentence, it has to kind of produce all of the salient things that were said. So it has to know that we're talking about objects 1 and 2, and they're small, and they're pyramids, and they are near object number 4, which happens to have the color blue and be block-shaped. And I think it's important to note at this point that it's not really a simple input-output mapping, because if we change the environment but keep the same auditory input, say, the answer will be different. So here the picture changed, the visual input changed, and we can see that at least part of the answer, the part where the network is picking out which objects the speaker is talking about, has to change as well. Okay, so now that I've given you an overview of the task that we're trying to get a neural net to do, I can kind of blow this up and show you the zoomed in version of the model. And here is where we get into why I'm part of this session. You can see up there that I'm using essentially the LSTM style of neural network, and maybe you can't read it up there, but it says it was developed by Schmidhuber and colleagues at IDSIA. So the idea here is that we have the objects coming in on the right side at the bottom, and we kind of accumulate those into a working memory with one of these self-recurrent layers of LSTM memory cell units. And we do something similar starting on the lower left, where the phonemes come in and get accumulated by 2 separate layers. Now we're using 2 layers there because the auditory input is starting at a much lower level, and we want to induce extra abstraction with the extra layers. Once we have working memory representations of both the visual and the auditory inputs, we can combine them in an integration layer that's also of LSTM units. And then we'll use the final representation on that layer to produce that sequence of predicates that we want to get out at the end.
So the visual stream, are you sending in a picture, or are you sending in the semantics?
It's essentially the semantics, yeah. So we could at some point take it down to using a pixel array or something, but we wanted to keep it kind of high in cognitive. We're really focusing on the auditory aspect of it.
So you're using that into a neural network? You're sending semantics?
Well, they're encoded as feature vectors essentially, right? So red is a feature and pyramid is a feature. So, but we imagine that that's the kind of representation that you would expect to be formed, further along the visual system. So here's some results from training a network in different contexts, and I want to draw your attention to the one on the right, which corresponds to that the strong systematicity notion that I was talking about earlier. After something like 3 million sentence scene presentations, the network is able to get 90%, 97% of brand new novel sentences correct, right? And these are sentences where one of the objects has never been seen before. Some of the phrases in the sentence have never been seen before. So we would like to think that this is pretty strong evidence that the network is able to come up with the systematic representation and really generalize what it's learned in a symbolic and compositional way. Kind of one last point is that we found it interesting to kind of decompose the task a little bit and look at how we fare on kind of the 2 subtasks, one of which is interpreting the language, which is to say, does the network know, what it means to be blue? Does it mean does it know what it means to be a pyramid, and so forth? Essentially, can it come up with the stuff that's highlighted in red there in the intention stream output sequence? And that corresponds to the solid line on this graph. So we can see that after only something like 20% of the training, it reaches ceiling on this part of the task. And at that point, as far as identifying the objects in the environment, as far as doing the actual grounding, right, in the vision, it's not doing very well. It's something like 70% accurate. And it takes the rest of the training time, an extra like 2.5 million scene sentence presentations before it gets there. So we think that that's pretty decent evidence that this grounding part of the task is hard, right? But at the same time, based on the arguments I've made earlier, we think that it's an essential part if you're going to have a general intelligence. So just to summarize, the contributions we have here, we've created this neural network system that is able to interpret essentially a speech stream, one step removed from an auditory signal, to produce the predicate-based meanings of an entire sentence and classes of sentences and brand new sentences. And at the same time, it kind of does this this cross-modal association and is able to pick out the visual reference of the sentence. So it grounds the words that it's learned in the vision. And it's also learning to generalize in a strongly systematic way, the kind of way that we expect a human to generalize, or that we expect a symbolic system to generalize. So we hope that by kind of solving these three problems with the neural network, we can potentially come forward in applying neural networks to AGI in the future. So that's me. Thanks.
So that was our last talk in this session. I would ask now the speakers of this session to come to the front and to take a seat for the questions.
This is a short question. Is for Tom. Well, your paper was really interesting. It's about interestingness, and the question is about: don't you think that your definition is a necessary condition but not sufficient, because you're not talking about any utility function? Because I might find something novel and ultimately comprehensible, but I'm not interested at all because this is not useful for me. So I'm not sure if you're just considering an absolute measure of interesting. Absolute is always relative, but just disregarding this utility thing. Can you comment on this?
I think there's a difference between interesting and useful. Some of the useful things we do are not very interesting, and some of the interesting things we do are not very useful. So I think those two concepts don't have to, I mean, there's an overlap clearly, but they don't have to be the same. So the utility doesn't have to get into the measure of interestingness. But I agree that, I mean, this is a very simple definition and a very simple measure. So it clearly can't capture everything. It captures one aspect of interestingness. So maybe there's others, and maybe utility can come in a different way. But I don't think it is necessary.
Okay, that was a short question. Thank you.
First, I have a very short remark regarding John Searle. You cited him as some kind of suggestion that we should do grounding, and I don't think that's what he did at all. I think he suggested not that we need to do grounding, but he suggested that we need not to do AI because computers cannot be intelligent. And this is where he wanted to go. If you want to suggest that we hook up computers to an external environment with visual data, in order to have representations that are grounded, you can cite Turing's 1950-something paper. He said that in there already. But Searle is one of the other side. He's on the dark side, basically.
Well, that's fair enough. And there's a lot of problems with the arguments that Searle makes, I think, as well. But the upshot that I got from studying him and studying that problem was, essentially that you couldn't do his Chinese room argument at all because of the grounding problem, right? I don't think that his idea that you could, contain in a book, in an oracle, the ability to have an intelligent conversation is misguided because it isn't grounded.
I'm very much tempted to ask Jürgen whether it's true that 1.16 of all people in Switzerland are in jail because of minor traffic violations. But what I really want to ask is, I really was very impressed by your results and your work and the way you did it. Do you think it's possible and meaningful to integrate this with existing cognitive architectures, for instance? Or is it something which you would suggest should scale up and replace cognitive architectures altogether as a guiding principle?
So as it stands now, I think it's a potentially useful ingredient for all kinds of architectures. I imagine, for example, a self-driving car like the ones of Ernst Dickmann's, which has a complex architecture for finding out salient points in the images. You are not looking at the entire visual scene. You are just you are pre-processing it, and then you find a couple of salient points, and that's where you focus. And then you still have to do this high-resolution pattern recognition. For example, it can be a small part of something like that. On the other hand, in the long run, I think this directing the attention, etc., is also going to be done by a system which has learned to do it well using reinforcement learning, as you are figuring out in the context of many, many different visual scenes, what is a good strategy of moving the eyes around to find the most informative points that you need to solve the current problem, or maybe just interesting points if you just want to have fun with in a museum, for example. So in the long run, I think we will have systems that are coming from the pixel level and scaling up all the way to the top. But for the moment, we should take advantage of the existing smart work that has been done and just plug it in wherever it's useful.
My question relates to this last question, this last answer. In the AGI in 2008, set up a situation where questioning whether you can scale up. If you learn single patterns, can you address multiple patterns? Because the multiple patterns quickly become a combinatorial explosion. If you know 100,000 things, there's about 5 billion two-pattern combinations, and so on and so forth. And segmenting out things in a scene, it's a little bit of a chicken and egg problem, because you don't know exactly how to focus your attention to a region if you don't know anything about the scene. So you have to know something about the scene, so then you have to deal with that. So it's kind of this back and forth. And I just wanted a comment. How do you think the networks so far will scale up to that? And how do you think you might be able to scale up to dealing with simultaneous things after you learn single patterns? That was a long question. I'm sorry.
So personally, I have great hopes that we will be able to deal with that problem just using this creative or curiosity principle, where you allow the system the additional freedom of posing itself its own tasks, which just are directed at better understanding the world. So yes, you are right. In the beginning, I don't know anything about this visual scene here, but at some point then, as I'm randomly motor babbling around, I see, oh, there are certain patterns. I get rewarded for discovering these patterns, which will lead me to certain behavioral strategies that I'm going to store and reuse in some sort of multi-modular reinforcement learning system. And then going from there, you will hopefully see this open-ended creation of novel behaviors, novel patterns being recognized, plus the strategies, the behaviors that lead to the creation of these novel patterns, such that the system is continually motivated to learn those things that are still easy to learn in addition to what it already knows. Always on this thin line where things are not yet too hard and not yet trivial relative to the current knowledge of the system. So I think this whole theory of curiosity and creativity business is going to help us along these lines, because it opens this additional degree of freedom of unsupervised active learning, where the system itself can measure how easy it finds to learn something, and how and to direct its attention to those things that are easily learnable in addition to what it already knows, as opposed to just trying to solve the externally posed tasks, which often are so complex that there's no chance of solving them immediately. Yeah.